Hey, P Statistics, welcome to Chapter 10, Section 2. We're going to get into comparing two means. So we're going to be doing the two sample t test and the two sample t interval in this section. By the end of this section, you should be able to describe the shape, center, and variability of the sampling distribution of x bar 1 minus x bar 2, determine whether the conditions are met for doing inference about the difference between two means, construct and interpret a confidence interval for the difference between two means, and calculate the standardized test statistic and p-value for a test about a difference between two means, and perform the full significance test about a difference between two means. So a lot of stuff that you knew probably was coming, hopefully. So for example, we're going to start with the sampling distribution. The heights of a 10-year-old girls can be modeled by a normal distribution with a mean of 56.4 inches and a standard deviation of 2.7 inches. So we've got that normal distribution. Then we've got the heights of 10-year-old boys can model with a normal distribution with this mean, a little bit lower. Boys are a little bit shorter there, but more variability, bigger standard deviation, still normal shape. So suppose we take independent simple random samples of 12 girls and 8 boys of this age and measure their heights. So what would these sampling distributions be? So the sampling distribution for the girls would be approximately normal because the population distribution was approximately normal. Even though we have a small sample size, remember that's another way we can reach normality, approximate normality. But the population was approximately normal, so we're good. The center would be at the same average for the girls, so mu sub x bar would be the same as mu sub g, which is 56.4. The standard deviation, well, that goes down based on the sample size. So that's sigma over root n, and so 2.7 over square root of 12 gives us that variability. And there are conditions for each of these. They mentioned this one here that's less than 10% of all girls, so yeah, that we do need that. Technically, we need this to be a nice random sample, which was mentioned, and then here our population was normal for our conditions. Same thing's true on the boys' side. All the same stuff, just dividing by square root of 8 instead for their standard deviation, but all the same conditions are met. So what can we say about the difference of x bar sub g minus x bar sub b in the sample means? And so they simulated a sampling distribution of those sample differences. And so if we focus on one little dot here, that had a difference of, so one set of samples gave x bar g of 56.09 and x bar b 54.68. So our average of our 12 girls was 56 inches. Our average of our 8 boys was 54 inches. If you subtract those two numbers, you get 1.41 inch difference. And so in that sample, those two samples, the difference in mean height was 1.41 inches. The girls were, on average, 1.41 inches taller. That's just one simulated out of many, many possible outcomes. We could see a bigger difference. We could see a smaller difference. We could even see a negative difference where the boys' average would be taller than the girls' average. So that's where that little value comes from. So the mean of this sampling distribution, the center is at 0.7 inches, and you would just get that by subtracting the two means. The standard deviation of this sampling distribution, this is what we get by adding the variances. So it was sigma over square root of n, and then plus sigma over square root of n. We add the variances. So we square both of those and divide, and then square both of those and then add them and then take the square root. And this is the formula that you get if you add variances. And so if you do this for those two sets, for those two standard deviations, you get 1.55 inches for the center and the spread. And of course, the shape is approximately normal. So the sampling distribution of x bar 1 minus x bar 2 follows these rules. So if you choose a simple random sample of size n1 from the first population with a mean mu1 and standard deviation sigma 1, and then an independent simple random sample of size n2 from population 2 with mean mu2 and a sigma 2, the sampling distribution of x bar 1 minus x bar 2 is normal either if both population distributions are normal, or is approximately normal if both sample sizes are large. Both sample sizes need to be at least 30 for central limit theorem. Or if one population is normally distributed and the other sample size is large. And then the other or they're not really mentioning here is that you can also check the graphs and make the assumption kind of thing we did where we'd make a box and whisker plot or a dot plot and say, yeah, it seems like the population might be close to normal and so we're good. So same conditions, just you have to do it for both samples. The mean of the sampling distribution of x bar 1 minus x bar 2 is mu1 minus mu2, as long as your sample means are unbiased, as long as you actually have random sampling, or we'll also kind of check the random condition for if we're doing experimental randomization. And then the standard deviation of the sampling distribution of x bar 1 minus x bar 2 is, you add the variances, you get this slightly ugly formula, not quite as ugly as our proportion formulas, as long as the 10% condition is met for both samples. Both samples are less than 10% of their respective populations. All right, so example problem, a fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with mean 27 ounces and standard deviation 8 ounces. When the medium setting is chosen, the amount of liquid dispensed, M, follows a normal distribution with mean 17 and standard deviation 5. To test the manufacturer's claim, the restaurant manager measured the amount of liquid in each of 20 cups filled using the large setting and 25 using the medium setting. Let x bar L minus x bar M be the difference in the sample mean amount of liquid under the two settings. So what is the shape of that sampling distribution of x bar L minus x bar M and y, and so on? We'll continue through each of these. So the shape will end up being normal because both population distributions are normal. The mean of that sampling distribution of x bar L minus x bar M will be just the two means subtracted. So the 27 and the 17 gives us an average difference of 10 ounces. That's what it should be, as long as we're not biased about how we get our sample. And then calculate and interpret the standard deviation of this sampling distribution. So we've got our standard deviations. So we're going to be doing the square root of, and then it's sigma squared over root n, or over n. Sorry, the root gets canceled out when you square it. So sigma squared over n plus sigma squared over n. So it's 0.8 squared over 20 for the first sample, and then 0.5 squared over 25, and you square root that, and you get 0.205 ounce. So note that we do not have to check the 10% condition because we're not sampling without replacement from a finite population. So in this case, we could continue, I guess, doing this machine I don't know. It's not really a finite population. We could keep doing it forever, I guess, as long as the machine doesn't break. And then finally, interpreting that standard deviation. So the difference tends to vary by about that much. So the difference, large cup minus medium cup, in the sample mean amounts of liquid typically varies by about 0.2 ounce from the true difference of 10 ounces.